Hello students, welcome to the digital classes. In the earlier classes, we have seen how electricity and magnetism are related, how magnetic field was produced by electric current. We have discussed how substances can be categorized based on magnetism. The substances which are strongly attracted by magnets are ferromagnetic substances, those which are weakly attracted by magnets are paramagnetic substances, and those which are weakly repelled by magnets are diamagnetic substances. We have seen the magnetic field around a bar magnet looks like this, and we observed the same pattern by using iron filings. We have seen how to draw magnetic field lines around a bar magnet by using a magnetic compass. We observed that magnetic field lines always form closed loops. This is because north pole and south pole always occur in pairs. The direction of magnetic field lines outside the bar magnet are from north pole to south pole, whereas inside the bar magnet the direction of magnetic field lines is from south pole to north pole, and we have seen that magnetic field lines will never intersect with each other. We have seen the direction to be represented by a dot which is out of the paper, and the direction into the paper must be represented by a cross. We discussed Oersted's experiment, wherein a magnetic compass which is placed close to a wire will show towards north when there is no current in the wire, whereas when there is current in the wire, the magnetic compass will get deflected. This shows that the current carrying wire has magnetic field around it. The magnetic field around a current carrying wire is given by right hand thumb rule, which says whenever we hold a current carrying wire by our right hand in such a way that the thumb shows the direction of the electric current, the curled fingers point the direction of magnetic field around the wire. When the current is out of the paper, the direction of magnetic field lines will be circular and the direction will be anti-clockwise. If current is into the paper, the magnetic field lines will be circular and the direction will be clockwise. We discussed the shape of magnetic field lines around a circular coil. When current is passed through a coil, which will produce magnetic field around it, and at the center the magnetic field will be straight and parallel to the axis. And we discussed the magnetic field lines around a solenoid. When current passes through the solenoid, magnetic field inside the solenoid will be parallel and will be parallel to the axis, whereas outside the magnetic field will be similar to that of a bar magnet. We discussed magnetic flux. The intensity of magnetic field lines passing through an area is called magnetic flux. SI unit of magnetic flux is Weber, and here the area must be perpendicular to the magnetic field. In case area is not perpendicular to the magnetic field, then we need to consider effective area. Effective area is the area perpendicular to the field. Effective area is given by the area times cos theta, where theta is the angle between magnetic field and the area. We discussed magnetic flux density. Magnetic flux density or magnetic field is nothing but magnetic flux per unit area. So, magnetic flux can be written as magnetic field into area. We discussed how an electromagnet can be made by using a solenoid. Electromagnet is a device that acts as magnet as long as we pass current and loses magnetism soon after we cut off the power supply. And to make an electromagnet, we need soft iron because it loses magnetism quickly when current is cut off. And when current is passed in the solenoid, the iron rod behaves as the magnet. This is a miniature electromagnet which we can make at home. We discussed magnetic force acting on a straight current carrying wire. A magnet experiences a force due to external magnetic field. As a current carrying wire acts as magnet, it also must experience a force in external magnetic field. A current carrying wire has its own magnetic field, and when it is placed in external magnetic field, both these magnetic fields interact, and as a result the wire experiences a force. The direction of current carrying wire can be known by right hand rule of positive charge, which says whenever we stretch three fingers, thumb, index finger and middle finger, such that three are mutually perpendicular to each other, in such a way that the index finger shows the direction of current or velocity of positive charge particle in external magnetic field, which is given by the middle finger. Then the thumb shows the direction of force acting on the current carrying wire or charged particle. Magnetic force on a straight current carrying wire or a positive charge particle in external magnetic field is in same direction. Consider a positive charge particle of charge q moving with velocity v in external magnetic field B. The direction of force acting on this positive charge particle can be known by right hand rule, and with that it will be downwards, and the magnitude of the force acting on the charged particle is given by BVQ, and if the angle between velocity and magnetic field is theta, then the force is given by BVQ sin theta. The motion of positive charge particle in external magnetic field will be circular. This is because the force is always perpendicular to the velocity, and hence the particle makes a circular motion. The direction of force acting on a current carrying wire can be known by right hand rule. Here the magnetic field is into the paper and current is upwards. By using right hand rule, we can find that the force acting on the wire will be towards our left. The magnitude of the force can be known by the formula F is equal to BIL, where B is magnetic field, I is current and L is length. We discussed DC electric motor runs because when current passes in the armature, the two arms will experience forces which are equal and opposite. These two forces will make the armature turn, and this makes the electric motor move. The speed of the rotation depends on the strength of the magnetic field, the area of the coil, the current in the coil and the number of turns in the coil. We have also discussed how a metal ring jumps off a copper coil. In this, when AC supply was given, the metal ring was jumped off. We discussed the difference between AC and DC. AC is alternating current and DC is direct current. In AC, the direction of current keeps changing alternately, and the supply which we get is 220 volts and 50 hertz, which means the direction of current changes 100 times every second. This is the graph of 3-phase AC power supply, whereas in DC the direction of current will be same, and DC current will be provided by sources like batteries. We discussed electromagnetic induction, which is the phenomenon of inducing current in the coil by changing the magnetic flux linked with the coil. We have seen the direction of the induced current will be in such a way that it always opposes the change that produced it. So, if there is a coil and a magnet close to it, as long as there is no movement, there will not be any kind of current induced. Whereas, if we make the magnet move close to the coil, there will be a current which will be induced and it will be anti-clockwise. The magnetic field produced by the induced current will always be opposite to that of the magnetic field of the magnet. Similarly, if we make the magnet move away from the coil in such a way that south pole faces the coil, then the direction of induced current will be anti-clockwise. In case north pole moves away from the coil or south pole moves towards the coil, the direction of induced current is same and it will be clockwise. So, this direction is due to Lenz's law. The direction of induced current is in such a way that it always opposes the change in the flux in the coil. We discussed Faraday's law of electromagnetic induction, which says the induced EMF is directly proportional to the rate of change in magnetic flux linked with the coil. Faster the flux changes, greater is the amount of EMF induced. So, the amount of EMF induced in a wire is given by BLV. We discussed applications of electromagnetic induction. Electromagnetic induction is used in metal detectors. Metal detectors will detect ferromagnetic materials by electromagnetic induction. Electromagnetic induction is also used in magnetic tapes to record data such as audio, video, and it can also be retrieved by the same principle. Electromagnetic induction can be used in encrypting data on ATM cards, and at the same time data can be retrieved by using electromagnetic induction in the ATM machine. Induction stove also works on the principle of electromagnetic induction. Electric generator works on electromagnetic induction. We discussed how electricity is generated in AC generator. This is the graph of the EMF induced in AC generator, and we also discussed how AC can be converted into DC in case of a generator by using a commutator, that is split rings. So, the direction of current will be same in case of a DC generator. Children, let us discuss Faraday's law of electromagnetic induction a little more in detail. Faraday's law of electromagnetic induction says the induced EMF is directly proportional to the rate of change in magnetic flux linked with the coil. The induced EMF is given by delta phi by delta t, where phi is the flux linked with the coil and t is the time. So, consider two wires which are connected to a galvanometer, which are placed in a magnetic field. We have another wire which is placed on these two wires, and when this wire moves, a current is induced in the wire. This is given by BLV. Children, let us derive how to get the expression EMF is equal to BLV. Now, let us consider a more simpler diagram and then let us derive. Here we have two wires which are connected to a galvanometer. Galvanometer is a device which will detect any small current in the wire. These two wires are placed in magnetic field, and a wire is placed connecting these two wires. The length of this wire is L, and the flux linked with this coil is given by B into A, that is magnetic field into area of the coil. So, area is length into S, where S is the distance the wire moves. So, as the wire moves, the magnetic field linked with the coil keeps decreasing. So, because of this motion of this wire, the flux linked with the coil is decreasing. This decrease in the flux will induce current. So, flux is given by B into L into S. So, change in flux is given by B into L into delta S. So, EMF is equal to delta phi by delta t. Substituting, we get EMF is equal to B into L into delta S by delta t. Delta S by delta t is velocity. So, we can replace delta S by delta t by V. So, EMF is equal to B into L into V, BLV. This is called motional EMF. Children, so we have seen the EMF induced in a wire is given by BLV, and this is only for one turn. Suppose if there are more turns in the coil, then the induced EMF will be multiplied by the number of turns. EMF is equal to delta phi by delta t. If there are n turns in the coil, then EMF is given by n times delta phi by delta t. Children, let us solve a numerical. Find the length of the conductor which is moving with the speed of 10 meters per second in the direction perpendicular to the direction of magnetic field of induction 0.8 t. If it induces an EMF of 8 volt between the ends of the conductor. So, in the question we have the data, velocity is equal to 10 meters per second, magnetic field is equal to 0.8 Tesla and induced EMF is equal to 8 volt. We know induced EMF is equal to BLV. So, substituting the values, 8 is equal to 0.8 into L times 10. This gives us length of the wire is equal to 1 meter. Children, let us solve another numerical. A charged particle Q is moving with the velocity with the speed v and perpendicular to the magnetic field of induction B. Find the radius of the path and time period of the particle. So, we know force is equal to BVQ or QVB. This force provides necessary centripetal force for the particle to make a circular motion. Centripetal force is given by mv square by r, where r is the radius of the circle. So, QVB must be equal to mv square by r. So, this force, because it is perpendicular to the direction of the velocity, the direction of the particle continuously changes because the force is always perpendicular to the velocity. This makes the charged particle make a circular motion. So, QVB is equal to mv square by r. So, r is equal to mv square by QVB, r is equal to mv by QB. So, the radius of the particle which is moving in a circular motion is given by r is equal to mv by QB. Children, let us solve another numerical. The magnetic flux inside a coil of 400 turns changes for each single turn with time as shown in the figure. Determine the maximum induced EMF generated in the coil and is there any change in the induced EMF from 0.1 second to 0.3 seconds. So, let us do the first one. Here the maximum EMF is induced from 0 to 0.1 seconds. This is because the time duration is less in this case, whereas from 0.3 to 0.45 the time duration is more for the same change in EMF. So, from 0 to 0.1 seconds we have change in flux is from 0 to 0.001 Weber. So, delta phi is equal to 0.001 Weber, time is 0.1 seconds and n is 400 turns. We know that EMF is equal to n times delta phi by delta t. So, EMF is equal to 400 times 0.001 by 0.1, which gives 4 volt. And coming to the next part, from 0.1 to 0.3 seconds the change in flux is 0 Webers, because the flux is constant which is equal to 0.001 Weber, there is no change in flux. So, there will not be any kind of induced EMF because change in flux is 0. So, children, we have understood that whenever there is a change in flux in a coil, EMF is induced. So, to have an induced EMF, it is necessary to change flux linked with the coil. So, this is how a dynamo works. In a generator, to have a current induced, we have to change magnetic flux linked with the coil. And so, as we change the flux linked with the coil, current will be induced in the coil, which we can use by connecting it to any device. Children, have you wondered how the lamps in vehicles get power? How the lamps in vehicles get electric power? All vehicles are equipped with a dynamo, and this dynamo will generate the power and it will recharge the battery, and battery supplies power to the lamps and other devices. Here is a generator, that is a dynamo in a car. This is connected to engine, and as the engine runs, this dynamo is rotated, and as it rotates, inside the magnetic field in the coil will change. As the magnetic flux linked with the coil changes, current is induced, and as it is connected to a battery, the battery gets recharged, and then from there the lamps and other devices will be supplied with the electric power. This is a dynamo for a bicycle. It is a small dynamo, and when it is connected to the tire, as the cycle runs, this dynamo is made to rotate. Inside there will be a coil and a magnet, and as the magnet rotates, the magnetic flux linked with the coil changes, and then current is produced and the bulb glows. Children, the electric generators work in a similar way. The only thing is the output power has to be much greater. For that, the generator and its armature coil has to be much bigger in size, and so a greater force is required to rotate the generator. So, we can use various forces to rotate the generator. We use kinetic energy of water stored in dams, or wind, or steam, or diesel or petrol engines to rotate the turbines and generate power. Here is a turbine, a generator. This turbine is rotated by means of water, and this will generate power. Here we have a steam powered generator, where the generator has to be rotated by using steam. Here we have a wind farm. Every windmill is equipped with the generator, and as the windmill rotates because of the wind, the power is generated inside the turbine, and when the speed of the wind is slow, very small amount of power will be generated. Hence, there will be so many windmills, and all of them will be connected in series, so that the induced EMF can be collected. Here is a dam, and when water is stored in the dam, using the kinetic energy of the water, the turbines will be rotated, and as the turbines rotate, electricity is generated. Children, now let us revise. We have discussed magnetic field around a bar magnet. We have observed how the magnetic field looks like by using iron filings around a bar magnet. We have seen how to draw magnetic field lines around a bar magnet by using magnetic compass. We discussed that magnetic field lines always form closed loops because north pole and south pole occur in pairs. We discussed the direction of magnetic field, which is produced by electric current in a wire. When we hold a current carrying wire by our right hand such that the thumb shows the direction of the current, the curled fingers will point the direction of magnetic field around the wire. If current is coming out of the paper, then the magnetic field around the current will be circular and the direction will be anti-clockwise. If the current is going into the paper, then the magnetic field lines will be circular and the direction of the magnetic field will be clockwise. We discussed the shape of the magnetic field lines around a circular coil. When current passes in a circular coil, at the center of the coil, the magnetic field will be parallel to the axis. We discussed the shape of the magnetic field lines around a solenoid. Inside the solenoid, the magnetic field lines will be parallel to the axis, and outside the solenoid, the magnetic field will be similar to that of a bar magnet. We discussed magnetic force acting on a straight current carrying wire. When a magnet experiences a force in external magnetic field, and as the current carrying wire also acts as a magnet, the current carrying wire should experience a magnetic force when placed in external magnetic field. This is because current carrying wire has its own magnetic field, and when it is placed in external magnetic field, both these magnetic fields interact and then there will be a force acting on the wire. This force acting on the wire can be known by right hand rule of positive charge, which says when three fingers, index finger, thumb and middle finger, are stretched mutually perpendicular to each other such that the pointer shows direction of current, the middle finger shows the direction of magnetic field, then thumb shows the direction of the force acting on the wire. Consider a positive charged particle which is moving with a velocity v in magnetic field B, then the direction of force acting on that charged particle is given by right hand rule and which will be downwards. The magnitude of the force acting on the charged particle is given by BVQ sin theta, where theta is the angle between the velocity of the charged particle and the magnetic field. The direction of magnetic force acting on a wire is given by right hand rule. Consider a magnetic field which is into the paper and let there be a wire, and then if there is no current flowing in the wire, there will not be any kind of force acting on it. But when the current is flowing upwards, by using right hand rule, we can find that the force will be towards the left. The magnitude of the force acting on the wire is given by BIL, where B is the magnetic field, I is the current and L is the length. We discussed magnetic flux density, which is magnetic flux per unit area. Magnetic flux density B is equal to phi by A, or phi is equal to B into A. We discussed the phenomenon in which electric current is induced in a coil by changing the magnetic flux linked with the coil is called electromagnetic induction. We discussed Lenz's law. The direction of the induced current is in such a way that it always opposes the change in the flux in the coil. We discussed Faraday's law of electromagnetic induction, which says the induced EMF is directly proportional to the rate of change in magnetic flux linked with the coil. Induced EMF is equal to delta phi by delta t, and if there are n turns, then the induced EMF is given by n times delta phi by delta t, where n is the number of turns. We discussed motional EMF, which is equal to BLV. We discussed AC electric generator, wherein an armature in presence of magnets is rotated, current is induced in the armature, and then which can be used by connecting using a load resistor. This is the graph of the current of the electric generator. Then to have current in single direction, we have to use a commutator, and in case if we use a commutator, then the current so produced will be direct current. So, this is a DC electric generator which will have an extra commutator only to change the direction of the current, so that the output current is always in the same direction. So, here you can see in the graph that always the direction of current is same. Children, we have come to end of this chapter electromagnetism. I would like you people to appreciate how electric field and magnetic field can be related, and one can be produced by using the other one. That is, electricity can be produced by magnetic field and magnetic field can be produced by electricity. So, I want you people to think over on how to produce electricity by various means by using magnetic field. We will meet in another lesson. Until then, thank you.